Now you understand how titration curves of or titration of amino acids is performed. What is happening at the molecular level, it's actually the same as what I discussed with the titration of the hydrochloric acid and the sodium hydroxide. Now we are ready to interpret the titration curves of amino acids. Let's take glycine for example. So this is the structure of the fully protonated glycine. So it has a positive charge, and with the first dissociation, we get the Zwitter ion, and after the second dissociation, we get a negatively charged form of glycine. Now, its titration curve looks like that of a diprotic acid. Glycine, the fully protonated form of glycine, is in fact a diprotic acid, right? Then we see a slight increase in pH, and then we see the buffer region due to the first dissociation of glycine. So the components in this buffer region include the Zwitter ion and the positively charged glycine. So at this region, specifically at the pK1 point here, we have equal amounts of the Zwitter ion and the positively charged glycine. Prior to the pK1 point, so in this region, we have more of the positively charged glycine and a little bit of the Zwitter ion. At pK1, we have equal amounts of the two, and if we increase the pH further, we will have more of the Zwitter ion and less of the positively charged glycine. And then we reach the equivalence point. So there's a steep change in pH. At this point, all of your positively charged glycine has been converted to the Zwitter ion. And then, if we increase the pH further, some of this Zwitter ion will be converted to the negatively charged glycine. So at this region, before the second pK, we have more of the Zwitter ion than the negatively charged glycine. And if we reach the second pK, we have equal amounts of the two. Beyond the second pK, we will have more of the negatively charged glycine, less of the Zwitter ion, and then we will have a second equivalence point. As we see here, the graph is supposed to show the inflection point, but the second equivalence point occurs at a pH at a very, very high pH, such that it is impossible to measure with a pH meter. That is why it's not visible in this titration curve. You might notice that the equivalence point is marked as Pi. This Pi is called isoelectric point. So the isoelectric point gives us the pH at which your amino acid is in its Zwitter ion form. So notice, right, between the two pK values, we see the Zwitter ion form of glycine. So the isoelectric point is determined by getting the average of the two pK values surrounding this Zwitter ion. So that's 2.34 plus 9.60 divided by 2. This will give us a value of 5.97. Meaning, if the pH of the solution is equal to 5.97, all of the molecules are in the Zwitter ion form. All of the molecules have a net charge of 0. Therefore, glycine will precipitate out of the solution.